Good afternoon. As we start Chapter 4 on ratios, I wanted to make a short video about the background knowledge that your student is expected to come into this chapter knowing. Now, a lot of these skills were expected to be picked up or acquired in 4th and 5th grade. And I understand that there are years that students lose stuff over the summer all the time and that this is a new program. So I wanted to give you information on what that is to hopefully help give you insight into the problems we will be solving in this unit. So the first skill that students are expected to come in with is expressing equivalent fractions through both multiplication and division. So first we will look at expressing them through multiplication. So if I have 5/7 and I want to write an equivalent fraction using multiplication, I need to pick a number that I'm going to multiply both the numerator and the denominator with. They need to be the same. We would have 10 over 14. Now, students can pick any number to multiply our fraction by, but these two numbers must be the same. These two things are the only thing that we're going to call the same in math this year, because 2 and 2 are identical. They are exactly the same. However, 5/7 and 10/14 are not identical. They're not exactly the same, but they are equal or equivalent, and they represent equal quantities. Okay, bringing it back to that quantity, we want to represent the same quantity a different way. So here, if we had 5/7, we would simply be chopping that 5/7 up into 10/14. Okay. 1, 2, 3, 4. Okay. And I apologize for the terrible representation there, but I think you get the idea. Now, scaling or writing equivalent fractions using division, if we started with 8 over 36, okay, and we want to divide them each by 3, which would give us 6 over 12. Now, students may see, oh, both of them are divisible by 6. And that would give us the fraction in its simplest form, or almost simplest, I suppose. We can divide by 3, and then we would have 1/2. Or it would be a quicker route to be in our simplest form. However your child does the steps, whether it be by 3, and then by 2, and then by 1, or divided by 3 and then have 1/2. Whichever way they do it is absolutely okay. They do not have to do it any special or certain way, so long as they know that they're building equivalent fractions. And you may even ask them, okay, what fractions here are equivalent? This really feeds into the next concept that we hope that they have a good grasp on when they come in, and that's writing fractions in simplest form. So if we have 12/16, we hope that students know they can divide each one by 4. And that would simplify this to 3/4. Now, oftentimes they'll start with 2. That's okay. Ask them if they start with 2. Oh. If they start with 2, I suggest, oh no, why doesn't it want to erase? Erase. Pause. Right, we're just going to write in a different color near that. If they want to start with 2, that's okay. We just, again, want to divide them or guide them and say, can we divide that by a number again? Are they both divisible by a number? Okay, and here's where we would ask, okay, can we divide it again? Okay, and if they say we can divide the 4, remind them that we have to divide both of the numerator and the denominator by the same number. One of the things that I see is they often are like, okay, I can divide this one by 6, and I can divide this one by 8. And that's going to give me 2 over 2, which, again, coming back to, it has to be the same number. We're scaling it down at the same rate. And a way to check would be, do our equivalent fractions represent the same quantity? Okay, so this is the fraction in simplest form. Usually, or it is when we have a prime in either the denominator or the numerator or in both. Okay, and are these equivalent? If we drew these in the same size fraction bars and cut them into equal sized pieces, would we have equal amounts? Now this is getting a little out of control, but that's just information so that you guys have that connection, because that's the connection we want them to start seeing. The last concept that I think they're all pretty familiar with is converting measurement, okay, given in one unit to a measure of another unit. Generally, I will give them measurement conversions that they don't know, but they will be given questions that look like, okay, how many inches are in 3 feet? Okay, and oftentimes it's nice to kind of pull out why this happens. So if you have 3 feet and you're cutting it into 12 pieces, it will be multiplied by 12. But as a student pointed out, when we were going over this in class, the way that they did it is they knew that they had their 3 feet, and they were dividing it by 12 inches, okay, or by 1/12, because now they're each in a size of 12. Each foot is in 12 pieces. So this again leads us back to the understanding of the keep flip change, where we're cutting each foot into 12 smaller pieces, so, and then we want to know how many groups of 1 there are in it. And we would have 36 over 1, which of course is equal to 36. Any way your child does it is totally, absolutely fine. Just sometimes they have a difficult time understanding what's going on. And if they have a difficult time understanding what's going on, ask them to draw the starting unit, or what we know. So if this is 1 foot, or this is representative of 1 foot, how many inches are in 1 foot? Well, if they know that there are 12 inches, then we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'll squeeze the 11th in here, and we'll erase this little part because I didn't mean to have that. And then they can see, oh, there's 12 inches in each foot, and if I have 3 feet, I can multiply 12. Let's use a different color, 12 by 3. Okay, or they can draw all 3. It's totally up to them. The final one that students may not be familiar with is interpreting a comparison bar model. This, I would say, is the most important because it's probably most likely the one they've had the least experience with. Now, we've been going over this in class today, and they actually thought it was fun. Yay, imagine that. That is wonderful news to me. And I am super glad that they all think that. So I am going to go over a couple of what these look like and of what is expected of them, so that when they come up or when you see them, you understand what they are. And if you see a word problem that they're doing that they're having a hard time with, where a bar model will be beneficial to use, then you can ask them, hey, can you use a comparison bar model to help you solve that problem? So all that they're asked to know when they come in to 6th grade about comparison bar models is understanding or interpreting missing quantities, essentially, and looking at it in a different light. So the first example I'm going to give is, we don't know the value of b, and we don't know the entire value of A. But we do know the value of this missing part is 12. Okay? When students see that this is 12, most of them will see, oh, this is 12. And if I split 12 into 2, this is 6, and this is 6. And this is 6, and this is 6, and this is 6, and that must mean these are all 6. So B must equal 18, and A must equal 30. We'll do a few more. And this is something super fun that you can practice at home, and I'm sure they would even love to make some for you to try. So the next one, let's look at quantity A and quantity B. So this tells us that the overall A plus B is equal to 35. But we don't know the value of B, and we don't know the value of A. So, sometimes it's hard for students to initially see or make sense of this, but we can always guide them and say, okay, well, if each box, if we have 5 boxes, and we know that all together the amount or the quantity within the boxes is 35, how can we figure out how much goes in each box? And usually very quickly they will be able to divide 35 by 7. If your child gets real caught up in computation, give them a calculator, again, because we want them to be looking at the relationship and the comparison and not caught up in the computation of it. Then they will be able to see that this is 21 and this is 14. Okay, let's Okay, so we don't know the value of A, and we don't know the value of B, but we do know that A has 18 more than B. And we also know that that 18 is equivalent to 3 boxes. So if we were to figure out the value of each box, we would need to divide 18 evenly into 3. We know that 18 divided by 3 is 6. So each of these boxes must be 6. And if that box is 6, then this box must be 6 as well, as must this box, because they are the same size. A will then be equal to 24, and B will be equal to 6. Total would be 30. And finally, the last example that I will do is this one. The last one, we have A, which consists of 3 units, and B, which consists of 4 units. And we want to see the value of, we want to find the value of each box, and then of A and B. And we already know the total. The total value of the sum of each of the boxes is 28. So if I have 1, 2, 3, 4, 5, 6, 7 boxes, and I need to divide them up 28 evenly amongst 7 boxes, I know that 28 divided by 4 is equal to 7. And we have 12 and 16, which equals 28. Now, one thing I will say is the kids love doing this. If you just draw one out and give them the missing piece or give them the full amount, they are super happy to do it, and you can even challenge them to make one for you. The students even made them without whole numbers and were able to solve them, and they get really excited, I think, because they get to find that missing piece, and it's more it's all visual. There's nothing to have to read and apply and figure out. It's all a visual thing. So hopefully that enthusiasm will carry into Unit 4, and I will continue to make videos about the problem solving as we go along. Thank you so much for everything, always, again.